Hello, welcome to week, I think, 14. And this week we're going to talk about fluids, but fluids are going to be a bit more difficult of a topic because you can't just use the same principles that you use for linear mechanics and sub in rotational values like we were for the past couple of chapters. So we have to actually talk about or like we did for not the past chapter, but the ones previous to those. So you have to uh talk about these different ideals and come up against them, but not there aren't a ton of references or examples in the book to go through, so I'm just going to try to explain all of these different theories and ideals the best I can, and then leave it to you in the homework to get more practice using them by themselves. So there are several states of matter, but there are three main ones. Solid, which has strong chemical bonds, which means that it has a set volume and shape. A liquid, which has weaker chemical bonds, has a set volume but no set shape. And gas, which has uh, negligible intermolecular bonds, but and no fixed shape or volume. But the molecules themselves can have bonds that uh, bind them to other atoms in the molecule. For example, ice is a solid state of water, which has both the bonds combining the H2O, the two hydrogens to the oxygen, and the bonds which combine the H2O to the other H2Os. And then a gas has negligible bonds connecting the H2O, the water vapor, to other water vapors, but it does still have those molecular bonds for the hydrogens and the oxygens. So liquid and gases are fluids, which basically can mean that can be defined as them having no set shape and being able to flow into different containers, or it can also be defined by their reaction to a shear force, which is instead of resisting the shear force and trying to maintain its shape, liquids and gases just you apply a shear force and the the molecules at the top of the system just move to accommodate the shear force instead of trying to resist them. So, one of the things that, since they don't have a solid uh, volume, or since they don't have a solid shape, uh, you can find different materials depending, or different properties of the material than you would if it had a if it was a solid and had a set volume and shape. So the way that we tend to uh talk about fluids and talk about like their properties, because this is something that can change depending on the shape or the temperature or another of other factors, is that instead of talking about uh for or area or volume or uh like the intermolecular bonds, we talk about the pressure, which is force divided by area. So pressure is just something that you can kind of see. So you can kind of you've experienced it when you're in a room with low atmospheric pressure versus high atmospheric pressure, or when you fill your cars up with a lot of gas, then that's going, or a lot of air. you fill your car tires up with that, and that's going to give you uh function pressure as a function of how much gas there is in there. So pressure is just a thing that we use to describe fluids. Basically, it's also mostly used this way because the a solid doesn't really change its force depending on the container it's in. It's just going to always have the force. But fluids such as water, we can have a cube full of water in a container of water. And what we're going to find is that this water, the pressure of the water depends on how deep you're going, which is also something that you see if you're swimming a lot. So pressure equals force over area. So the amount of pressure, uh, the amount of force on this block is going to be the weight pressing down. Uh, yeah, it's going to be the weight pressing down from the top of the block and then from the bottom of the block. So the pressure at the force at the top is equal to P naught times A, and the force at the bottom is equal to F naught, which is P naught A, plus uh, M times G, where M is the mass of the water in the block. So there's going to be more force pushing down at the bottom of the block because there's more water on top of the material or on top of this cross-sectional area that you're looking at. So this is going to be equal to P naught A plus P or rho times A times the height of the block times G. And then this is just the mass, where rho is dV, or sorry, that's the opposite. Rho is dm dV. It's just it's called the density, and it's just the amount of a mass there is in it's inside of a unit volume. So the as dV goes to as the volume goes to infinity or infinitesimally small, how much mass is in that volume. So P times A equals P naught A plus rho G H A. So P of H is equal to P naught plus rho G H. And then where H, oh, and then another thing that I should bring up before I go on is that H has a positive value. H is depth. So it has a positive value the farther down you go. So the farther down you go, the more pressure there is. Okay, so that's the one of the main things that you're going to learn generally. So this is for liquids, and it is also true of gases to a much lesser extent because rho for a gas is generally a lot less than rho for a liquid. So this difference is takes a lot more to notice. But when we're talking about gases, we have the ideal gas law. So PV equals uh nRT, where N is the number of moles, R is the uh I don't remember what R is called. It's Boltzmann's constant divided by 6 point, or the number of atoms in a mole, and then T is the temperature in Kelvin. So PV equals N times KBT, where N is going to be the number of atoms, not the number of moles, and KB is the Boltzmann constant, which connects temperature to energy by doing a unit conversion, basically. So temperature, you can argue, is a unit of energy by itself, but uh, the Boltzmann constant converts it from uh, Kelvin to joules. So P is equal to N divided by V, KBT, and then N times rho times V is equal to the mass. So M, oh, I forgot to write it down. Okay. So yeah, N times rho times V is equal to M. Actually, yeah, so this isn't in the book, so I'm going off my own intuition here, but uh mass is equal to rho times V. So 1 over V is equal to rho over mass. And then N is just uh yeah, and then N is just there to help you with counting. So I don't know if I went over this, but this is the ideal gas law, which you've probably learned in high school chemistry. And we're going to learn more specifically, but I just wanted to go over this right now so I could talk about the pressure at various elevations for gas. So we remember from P equals P equals rho GH, that rho that dp dt d x dz is negative rho times g times dh dh, because as h increases yeah, as h increases uh it's going down. It's going to a lower to a higher pressure. So it's going to have a negative there instead of just the positive value that you would see otherwise. So dpd z equals negative rho g. Rho equals negative dp dz over times 1 over g. So p equals rho over m times kbt is equal to negative dp dz times kbt over mg. So p dp dz equals negative mg over kbt uh p. So p is equal to e to the negative mg over kbt times p naught. So if you don't believe me about this, then just dp dz is again going to be p naught times negative m. Oh, oh yeah, mgz over negative mgz over kbt. So negative times negative mg over kbt times e to the negative mgz over kbt equals negative mg over kbt p. So dpdz is proportional to negative p, which means that it's an exponential function, which means that it's described by this equation right here. And then that's interesting and everything. But let's move on to. Oh no. And then another thing to note is that so this is all in your textbook, and I would recommend just going through your textbook as well as going through the lecture notes. But one thing to note is that since uh fluids are either resistant to or susceptible to shear forces, depending on how you look at it, all pressure is going to be pointing perpendicular to the surface, because any pressure that doesn't point perpendicular to the surface is going to cause a shear force, which is going to cancel, going to make it so that the uh, pressure and the fluid rearranges itself so it is pointing perpendicular to the surface. Uh, so and then P, let's also just briefly derive gauge pressure, where P absolute is equal to P gauge plus rho atmosphere, or not rho atmosphere, P atmosphere. So P gauge plus P atmosphere. So basically what this means is that if you talk about pressure, then you're usually talking about the difference in force from outside to inside. So if you blow up a tire, then the gauge pressure is going to tell you how much force the tire is exerting inside than the amount of force that's being exerted outside by the atmosphere. So the absolute value of pressure is going to be equal to the gauge pressure plus P, the pressure from the atmosphere. So gauge pressure is just a way that we talk about pressure to yeah, we talk about pressure to talk about the difference in pressure instead of just the absolute pressure versus if you were in a vacuum, if you were in space or anything like that. And then yeah, I'm going to take a break. I'll be back soon with next section.